All right, so today what I'm going to do, I'm going to very quickly show you how to use the Kelter strategy. It's an amazing strategy for how to do Lewis structures. And in order to be able to do this, you need to be able to feel very comfortable with your periodic table. Let me remind you a couple things. If you look at your periodic table, the first column has one valence electron, this whole column. This one has two. We really don't care about this middle part. Who cares? And then we go 3, 4, 5, 6, 7, and 8, remind ourselves that this actually belongs over here. So we can look at any element and know exactly how many valence electrons that element has, and that's going to be important in just a second. The other thing you might want to do is you might want to pull out these notes right here. These are in your folder under Unit 6, and you can take a look at these, and you can, as we're going through this, you might want to follow along. So let's just jump right in, and the best way to do this is to start with an example. So we're going to start with the example of NO3 minus. And I'm going to use an example that even has a minus in here so that we can give you the highest level of difficulty. So the very first thing we're doing in every single one of these problems is we're going to figure out the valence electrons, the number of valence electrons. And the valence electrons are simply, you look up each of these elements on the periodic table. So N, if you take a look at it, it is in the 1, 2, 3, 4, 5th column. So N has 5 valence electrons. O, which is right next to it, has 6. But there are 3 of these O's in here. So we go 3 times 6. Evidently, I've not drawn with this for a while, so it's a little bit clunky. The other thing you need to be aware of is this, and this says it right here. If the molecule has a negative charge, which this one clearly does, the only place that impacts us is if we is when we add to our valence electrons. So if we have a minus here, the same as saying minus 1, isn't it? So that minus 1 means we're going to add one more valence electron to our valence electrons. If it was a minus 2, that'd be a minus 2. It would be a plus 2. If it's a minus 3, it would be plus 3. And heaven forbid we had a plus 1, we'd actually subtract an electron away. And that's important because if we add 5 plus 3 times 6, that's 23. If we left it at 23, this, by the way, is 23, plus 1. If we left it at 23, we'd have an odd number, and that is problematic for us. So the valence electrons in this case are going to be 24. Now, again, part of what we're doing with this strategy, it's kind of like a magic trick to figure out the number of bonds so that we can draw a structure. So let's move on to my most favorite part, and that is happy electrons. So what we're going to do is we're going to take a look at each of these atoms, and if you take a look here, we have 1, and then aren't there 3 of these atoms over here? So altogether, don't we have 4 atoms, right? And one of the things we've talked about a lot in class is how many electrons does it take to make an atom happy? And in the periodic table, every single atom on the periodic table, every one of them on here, except for the first 5, and I'm going to shade in these first 5, 4, 5, all of these, and that's probably the worst way to do it. I probably should have just circled this because they're not supposed to be scratched out or anything. So let's do this. Horribly enough. These ones right here, they only want to have 2 electrons to be happy. Every other one on the periodic table wants to have 8. So the game we're going to play is really simple. How many of these atoms in this molecule are part of the first 5? Now, if I hadn't scratched in and you could actually see what I was writing here, you discover that all 4 of these atoms are not part of these first 5, which means that all 4 of these want to have 8 electrons to be happy. So in order to do our happy electrons, we go 4, which the number of atoms we have, times 8, and our value ends up being 32 electrons. So we want to have 32 electrons overall to be happy. And again, happy electrons really aren't a thing, but it helps us to do this method. Now, step number 3 is this. We take the number of electrons we had from our happy, and we subtract our valence, and we divide by 2. So this is my happy minus valence divided by 2. Now, just to go back so we can remember it, for our happy, we had 24 electrons. For our happy, we had 32 electrons. For our valence, we had 24. So wouldn't that be then 32 subtract 24, and when we divide it by 2, that gives us 4 bonds. This is the most important thing here because, I don't know why that did that, but we want to know the number of bonds, and the number of bonds are equal to our happy minus valence divided by 2. And that tells us this right here, that we need to have 4 bonds in our final structure, and that is enormous. So what do we do next? We want to kind of draw a skeletal structure of the whole thing. So we have to choose a central atom. Now, just by process of elimination, doesn't it kind of look like this guy should go in the middle? Now, if we had a carbon, this would be really simple because carbon owns everything. Carbon always goes in the middle. In this case, we don't. We have a nitrogen and an oxygen. If we take a look here, this is our nitrogen over here, and this is our oxygen. Now, you should know this. Fluorine is the most electronegative atom on the periodic table. The closer you are to fluorine, the more electronegative you are. And the reason we say that is that if you take a look up here, we want to put the least electronegative atom in the center. Of course, we can't put hydrogen in there because it only has one electron able to bond. But if we compare these two, nitrogen and oxygen, it just turns out that nitrogen is farther away from fluorine, and therefore it has a lower electronegativity, which means we're going to put it in the middle. So we're going to choose nitrogen. We know that nitrogen's going in the center, and so let's move forward, and we're going to draw kind of a skeletal structure. So what I'm going to do is I'm going to put an N in the middle, and then I'm going to draw my O's around the outside. Now, it doesn't really matter where you put them, but just think of this kind of like a square, and we want to put an O on each side, 3 O's altogether, so 1 O on each side and leaving 1 blank. If you decided, you know what, I really feel like putting an O up here on the top, have at it, my friend. It does not matter where you put them. But it doesn't matter that you attach everything to the center. So we're going to go 1 right here, 1 right here, and 1 down below. Now, if you take a look at this, super, we've attached everything in, but the thing that really mattered to us, if we look back, didn't we come over here and didn't we say that we needed 4 bonds in our final structure? And that's enormous. So if we go ahead, we need to put 4 bonds in here, and then we've only put in 3. So what do? We need to pick one of these attachments and make it a double bond. I'm going to choose this one over here because I can, but you could have chosen either of these other two as well. That's kind of a big deal. And right now we have the base skeleton of our structure. Now, what do we do next? Well, I'm going to redraw this here, and you know what? I'm going to just go over here and put the oxygen over here because I want to prove to you that it doesn't matter where we put our 3 things. You notice how I put the things on the top here? It's super fun. So the next thing we do is we need to make sure that every atom in our particular molecule has a full outer shell of 8. Now, what you should remind yourselves of, and we talked about this again in class, is that each one of these bonds, it counts as 2 electrons that are being owned, I did air quotations if you couldn't see me down below, by the atom that they're touching. So this nitrogen right here has 2, 4, 6, 8 electrons that are surrounding it that it claims ownership of. We call it the toddler principle of ownership. Even though it's sharing these 2 electrons, every single time it writes a bond, it actually claims ownership of them. So this nitrogen in the middle is pretty happy because it has 8 valence electrons. Now, this oxygen over here, do you see how there's just 2, one here, and one right here? There's only 2 bonds, which means if you think of a bond as 2 electrons that are being shared, there's only 4 electrons that are being shared, which means that it's missing 4 electrons. So when we talk about completing the octet up here, what we really mean is saying draw dots, draw lone electron pairs to make sure that every atom has a full outer shell. So I'm going to go over here, and since there's only 4 right here, I'm going to go 5, 6, 7, 8. Again, it doesn't matter where you put them, but we like to put our electrons in pairs. Up here, do you see how we only have 1 single bond right here? That counts as 2 electrons towards both the oxygen and the nitrogen, but we care about the oxygen right now. That means we have 6 that we're missing, and we're going to go 1, 2, 3, 4, 5, 6. And this is exactly the same as this, so I'm going to do the same thing. 1, 2, 3, 4, 5, 6. So altogether in my structure, I have made 8 electrons in each one. Let me count them again. 2, 4, 6, 8 around this oxygen. 2, 4, 6, 8 around this oxygen. 2, 4, 6, 8 around this oxygen. And around the nitrogen in the middle, I have 2, 4, 6, and 8, which is super. Now, the last step is that we need to verify what we've done. Now, I'm going to draw this again really quickly because I can. And I'm going to put my electrons like this. I'm going to put a pair of electrons over here. I'm going to put my nitrogen with an oxygen on the top. I'm going to draw my 6 dots around it. And I'm going to draw my 6 dots around this. Now, one of the things you need to remember from the very beginning that our valence electrons, they were set at 24. So let me just remind you this. Valence 24, happy 32. I don't know why we gave it a third eye. And the number of bonds was 4. But we care about the bonds more than anything. I'm sorry, about the valence electrons more than anything. So we care about this. That means when we add up all the electrons in this structure, it has to equal 24. So if we go like this, we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And this is a good structure because every one of these has a full outer shell of 8, and altogether when we add them up, it equals 24. So this is the correct Lewis structure. But there is one more thing we need to do. Anytime that you see a polyatomic ion, and what that is, this right here is a polyatomic ion. This is something that has, the entire molecule has a charge on it. So when we draw our final Lewis structure, you must, in order to let everyone know that there's an extra negative, you must put square brackets around the entire thing and a minus on the outside. This right here is how we would draw NO3 minus. Now, I would love for you guys to stay tuned because this is part 1 of the Lewis structure drawing. We're going to deal with exceptions and some other things in the future, but hopefully this is of help. And if you need to, let me know and come by either before, at lunch, or after school, and I can help you with any problems you're having. Hope you have a great night. Take care.